Hi everyone, welcome back to Midnight History. It's always a joy to know you're here, listening, dreaming, and wandering through time with me once more. If you love quiet stories, hidden truths, and the strange beauty of our universe, make sure to subscribe and stay close so Midnight History can find you again when the next midnight comes. Now take a deep breath, relax, and let's begin tonight's story. Tonight we journey into the mind of one of humanity's greatest thinkers, Albert Einstein, a man whose ideas bent space, stretched time, and changed how we see the universe forever. From the speed of light to the fabric of reality itself, his mathematics revealed a world far stranger than anyone imagined. So what really happens when you follow Einstein's math? Stay with Midnight History and let's uncover the beautiful, impossible truths that lie beyond the equations. It also implied the existence of parallel universes and even possibly a way to travel between them. This is a video about the real science of black holes, white holes, and wormholes. The general theory of relativity arose at least in part due to a fundamental flaw in Newtonian gravity. In the 1600s, Isaac Newton contemplated how an apple falls to the ground, how the moon orbits the Earth and Earth orbits the sun, and he concluded that every object with mass must attract every other. But Newton was troubled by his own theory. How could masses separated by such vast distances apply a force on each other? He wrote that one body may act upon another at a distance through a vacuum without the mediation of anything else is, to me, so great an absurdity that I believe no man who has a competent faculty of thinking could ever fall into it. One man who definitely had a competent faculty of thinking was Albert Einstein, and over 200 years later, he figured out how gravity is mediated. Bodies do not exert forces on each other directly. Instead, a mass like the sun curves the space-time in its immediate vicinity. This then curves the space-time around it, and so on all the way to the Earth. So the Earth orbits the sun because the space-time Earth is passing through is curved. Masses are affected by the local curvature of space-time, so no action at a distance is required. Mathematically, this is described by Einstein's field equations. Can you write down the Einstein field equation? This was the result of Einstein's decade of hard work after special relativity, and essentially what we've got in the field equations. On one side it says, tell me about the distribution of matter and energy. The other side tells you what the resultant curvature of space-time is from that distribution of matter and energy. And it's a single line. It looks like, oh, this is a simple equation, right? But it's not really one equation. It's a family of equations. And to make life more difficult, they're coupled equations. So they depend upon each other and they are differential equations. So it means that there are integrals that have to be done. So there's a whole bunch of steps that you need to do to solve the field equations. To see what a solution to these equations would look like, we need a tool to understand space-time. So imagine you're floating around in empty space. A flash of light goes off above your head and spreads out in all directions. Now your entire future, anything that can and will ever happen to you, will occur within this bubble, because the only way to get out of it would be to travel faster than light. In 2 dimensions, this bubble is just a growing circle. If we allow time to run up the screen and take snapshots at regular intervals, then this light bubble traces out a cone, your future light cone. By convention, the axes are scaled so that light rays always travel at 45 degrees. This cone reveals the only region of space-time that you can ever hope to explore and influence. Now imagine that instead of a flash of light above your head, those photons were actually traveling in from all corners of the universe, and they met at that instant and then continued traveling on in their separate directions. Well, in that case, then into the past, these photons also reveal a light cone, your past light cone. Only events that happened inside this cone could have affected you up to the present moment. We can simplify this diagram even further by plotting just one spatial and one time dimension. This is the space-time diagram of empty space. If you want to measure how far apart 2 events are in space-time, you use something called the space-time interval. The interval squared is equal to minus dt squared plus dx squared Since space-time is flat, the geometry is the same everywhere. And so this formula holds throughout the entire diagram, which makes it really easy to measure the separation between any two events. But around a mass, space-time is curved, and therefore you need to modify the equation to take into account the geometry. This is what solutions to Einstein's equations are like. They tell you how space-time curves and how to measure the separation between two events in that curved geometry. Einstein published his equations in 1915 during the First World War, but he couldn't find an exact solution. Luckily, a copy of his paper made its way to the Eastern Front, where Germany was fighting Russia. Stationed there was one of the best astrophysicists of the time, Carl Schwarzschild. It's pretty simple and makes intuitive sense. Far away from the mass, space-time is nearly flat. But as you get closer and closer to it, space-time becomes more and more curved. It attracts objects in, and time runs slower. Gunshots firing. Schwarzschild sent his solution to Einstein, concluding with, "The war treated me kindly enough in spite of the heavy gunfire to allow me to get away from it all and take this walk in the land of your ideas." Einstein replied, "I have read your paper with the utmost interest. I had not expected that one could formulate the exact solution to the problem in such a simple way. But what seemed at first quite simple soon became more complicated." Shortly after Schwarzschild's solution was published, people noticed two problem spots. At the center of the mass, at r equals 0, this term is divided by 0. So it blows up to infinity, and therefore this equation breaks down and it can no longer describe what's physically happening. This is what's called a singularity. Maybe that point could be excused because it's in the middle of the mass, but there's another problem spot outside of it at a special distance from the center, known as the Schwarzschild radius. This term blows up. During its lifetime, the inward force of gravity is balanced by the outward radiation pressure created by the energy released through nuclear fusion. But when the fuel runs out, the radiation pressure drops. So gravity pulls all the star material inwards, but how far? Most astronomers believed some physical process would hold it up. And in 1926, Ralph Fowler came up with a possible mechanism. Pauli's exclusion principle states that fermions like electrons cannot occupy the same state. So as matter gets pushed closer and closer together, the electrons each occupy their own tiny volumes. But Heisenberg's uncertainty principle says that you can't know the position and momentum of a particle with absolute certainty. So as the particles become more and more constrained in space, the uncertainty in their momentum, and hence their velocity, must go up. So the more a star is compressed, the faster electrons will wiggle around, and that creates an outward pressure. This electron degeneracy pressure would prevent the star from collapsing completely. Instead, it would form a white dwarf with a density much higher than a normal star, and remarkably enough, astronomers had observed stars that fit this description. One of them was Sirius B, but the relief from this discovery was short-lived. 4 years later, 19-year-old Subramanian Chandrasekhar traveled by boat to England to study with Fowler and Arthur Eddington, one of the most revered scientists of the time. During his voyage, Chandrasekhar realized that electron degeneracy pressure has its limits. Electrons can wiggle faster and faster, but only up to the speed of light. That means this effect can only support stars up to a certain mass, the Chandrasekhar limit. Beyond this, Chandrasekhar believed not even electron degeneracy pressure could prevent a star from collapsing. But Eddington was not impressed. He publicly blasted Chandrasekhar, saying, "There should be a law of nature to prevent a star from behaving in this absurd way." And indeed, scientists did discover a way that stars heavier than the Chandrasekhar limit could support themselves. When a star collapses beyond a white dwarf, electrons and protons fuse together to form neutrinos and neutrons. These neutrons are also fermions, but with nearly 2,000 times the mass of an electron, their degeneracy pressure is far stronger. And that's what keeps neutron stars from collapsing under their own gravity. For a long time, scientists were convinced that somehow, even if they didn't fully understand the mechanism, something would always stop a star from collapsing into a single point. After all, the very idea of a black hole seemed far too absurd to be real. But that belief was shattered in the late 1930s, when J. Robert Oppenheimer and George Volkoff discovered that neutron stars also have a maximum mass, a limit beyond which even degeneracy pressure cannot hold them up. Soon after, Oppenheimer and Hartland Snyder demonstrated that for the most massive stars, once their fuel runs out, nothing can save them. They wrote chillingly, "This contraction will continue indefinitely." Yet Einstein still refused to believe it. Oppenheimer argued that stars could collapse without end. But when Einstein examined the equations, he saw that time itself freezes at the event horizon. To him, that meant nothing could truly fall in, suggesting either there was something missing in our understanding or that black holes simply couldn't exist. But Oppenheimer had an answer to that mystery. He said to an outside observer, "You could never see anything go in, but if you were traveling across the event horizon, you wouldn't notice anything unusual, and you'd go right past it without even knowing it." So how is this possible? We need a space-time diagram of a black hole. On the left is the singularity at AR equals 0. The dotted line at AR equals 2m is the event horizon. Since the black hole doesn't move, these lines go straight up in time. Now let's see how ingoing and outgoing light ray travel in this curved geometry. When you're really far away, the future light cones are at the usual 45 degrees. But as you get closer to the horizon, the light cones get narrower and narrower, until right at the event horizon, they're so narrow that they point straight up and inside the horizon. The light cones tip to the left, but something strange happens with ingoing light rays. They fall in, but they don't get to R equals 2m. They actually asymptote to that value as time goes to infinity, but they don't end at infinity, right? Mathematically, they are connected and come back in, and they're traveling in this direction, and this bothered a lot of people. This bothered people like Einstein, because he looked at these equations and went, well, if nothing can cross this sort of boundary, then how could there be black holes? How could black holes even form? So what is going on here? Well, what's important to recognize is that this diagram is a projection. It's basically a 2D map of four-dimensional curved spacetime. It's just like projecting the 3D Earth onto a 2D map. When you do that, you always get distortions. There is no perfectly accurate way to map the Earth onto a 2D surface, but different maps can be useful for different purposes. For example, if you want to keep angles and shapes the same, like if you're sailing across the ocean and you need to find your bearings, you can use the Mercator projection. That's the one Google Maps uses. A downside is that it misrepresents sizes. Africa and Greenland look about the same size, but Africa is actually around 14 times larger. The Gall-Peters projection keeps relative sizes accurate, but as a result, angles and shapes are distorted. In a similar way, we can make different projections of 4D spacetime to study different properties of it. Physical reality doesn't change, but the way the map describes it does. He had chosen to put a particular coordinate system of a space and have a time coordinate, and off you go. It's the most sensible thing to do, right? Derek, people realize that if you choose a different coordinate system by doing a coordinate substitution, then the singularity at the event horizon disappears. It goes away. That problem goes away, and things can actually cross into the black hole. What this tells us is that there is no real physical singularity at the event horizon. It just resulted from a poor choice of coordinate system. Another way to visualize what's going on is by describing space as flowing in towards the black hole, like a waterfall. As you get closer, space starts flowing in faster and faster. Photons emitted by the spaceship have to swim against this flow, and this becomes harder and harder the closer you get. Photons emitted just outside the horizon can barely make it out, but it takes longer and longer. At the horizon, space falls in as fast as the photons are swimming. So if the horizon had a finite width, then photons would get stuck here, photons from everything that ever fell in, but the horizon is infinitely thin. So in reality, photons either eventually escape or fall in. Inside the horizon, space falls faster than the speed of light, and so everything falls into the singularity. So Oppenheimer was right. Someone outside a black hole can never see anything enter, because the last photons they can see will always be from just outside the horizon. But if you yourself go, you will fall right across the event horizon and into the singularity. Now you can extend the waterfall model to cover all three spatial dimensions, and that gives you this, a real simulation of space flowing into a static black hole made by my friend Alessandro from ScienceClick. Later, we'll use this model to see what it's like falling into a rotating black hole. Now, I've never been sucked into a black hole, but sometimes it feels like it when I'm stuck on the phone with a spam caller. Fortunately, today's sponsor Incogni can help. I used to get several spam calls a day, and they frustrated me so much that I wrote a letter to the Do Not Call registry to get my number removed, but that didn't work, and so I wanted to go on the offensive. I even contemplated making a video where I just mess with spam callers to get some revenge for all the frustration and lost time. But I no longer have to do that thanks to Incogni. There are a lot of data brokers out there that suck up information about you, a bit like a black hole. They collect things like your name, phone number, email address, and even your social security number, and then they sell this information on the open market, which is why we often get calls from people that we've never even given our number to. Incogni battles these data brokers. You simply give them permission, and they figure out who out there has your data, which laws apply, and then they send them the right letter with the correct legal terms to each data broker with the request to remove your information. Now, you could do this yourself, but it's a super tedious process that would take days, weeks, even months, and then you'd have to keep doing it forever. So that's something I definitely don't have the time and energy for. But Incogni makes this really easy. Just sign up and they'll give you a list of companies that have your data, the severity of each claim, and the status of each request. So far, they have filed 126 requests for me, 83 of which have been completed, saving me over 62 hours of work. But the best part is since I signed up, I've hardly gotten any more spam calls. So to try Incogni and fight against the data brokers, visit incog.com.veritasium. You can click that link down in the description or scan the QR code right here and make sure to use the code Veritasium to get 60% off. So head over to incog.com.veritasium to get started. I want to thank Incogni for sponsoring this part of the video, and now back to space-time maps. If you take this map and transform it so that incoming and outgoing light ray all travel at 45 degrees like we're used to, then something fascinating happens. The black hole singularity on the left transforms into a curved line at the top, and since the future always points up in this map, it tells us that the singularity is not actually a place in space. Instead, it's a moment in time, the very last moment in time for anything that enters a black hole. The map we've just created is a Kruskal-Szekeres diagram, but this only represents a portion of the universe, the part inside the black hole's event horizon and the part of the universe closest to it. But what we can do is contract the whole universe, the infinite past, infinite distance, and infinite future, and morph it into a single map. It's like using the universe's best fisheye lens. That gives us this Penrose diagram. Again, light rays still always go at 45 degrees, so the future always points up. The infinite past is in the bottom of the diagram. The infinite future at the top and the sides on the right are infinitely far away. The black hole singularity is now a straight line at the top, a final moment in time. These lines are all at the same distance from the black hole. So the singularity is at r equals 0. The horizon is at ER equals 2m. This line is at ER equals 4nm, and this is infinitely far away. All of these lines are at the same time. What's great about this map is that it's very easy to see where you can still go and what could have affected you. For example, when you're here, you've got a lot of freedom. You can enter the black hole or fly off to infinity, and you can see and receive information from this area. But if you go beyond the horizon, your only possible future is to meet the singularity. You can still, however, see and receive information from the universe. You just can't send any back out. Now think about being at this point in the map. This is at the event horizon, and now your entire future is within the black hole. But what is the past of this moment? Well, you can draw the past light cone, and it reveals this new region. If you're inside this region, you can send signals to the universe. But no matter where you are in the universe, nothing can ever enter this region because it will never be inside your light cone. So things can come out, but never go in. This is the opposite of a black hole. a white hole. What color is a white hole? Geraint exhales. Derek laughs. I mean, it's not gonna have a color, right? It's gonna be whatever's being spat out of it. Derek, now, we've been showing things being ejected to the right, but they could just as well be ejected to the left. So what's over there? This line is not at infinity, so there should be something beyond it. If we eject things in this direction, you find that they enter a whole new universe, one parallel to our own. Geraint, we can fall into this black hole, and somebody in this universe here could fall into this black hole in their universe, and we would find ourselves in the same black hole. Derek chuckles. The only downside is that we'd both soon end up in the singularity. I guess I'm just trying to understand where that universe appears in the mathematical part of the solution. Like, can you point to the part of the equation and be like, so that's our universe, and then these terms here, that's the other universe? Or do you know what I mean? Like, yeah, well, it's coordinates, right? Imagine somebody, right, came up with a coordinate system for the Earth, but only the northern hemisphere, and you looked at that coordinate system, right? And you looked at it and you said, I can see the coordinate system, it looks fine. But mathematically, latitudes can be negative, right? You've only got positive latitudes in your solution. What about the negative ones? And they said to you, scoffs, negative ones? No southern hemisphere, right? And you've got to go, well, the mathematics says that you can have negative latitudes. Maybe we should go and look over the equator to see if there is something down there. And I know that's a kind of extreme example, because we know we live on a globe, but we don't know the full geometry of what's going on here, in the sense that Schwarzschild laid down coordinates over part of the solution. It was like him only laying down coordinates on the northern hemisphere, and other people have come along and said, hey, there's a southern hemisphere. And more than that, there's two Earths. That's why it's called maximal extension. It's like, if I have this mathematical structure, then what is the extent of the coordinates that I can consider? And with the Schwarzschild black hole, you get a second universe that has its own independent set of coordinates from our universe. I want to emphasize, right, this is the simplest solution to the Einstein field equations. And it already contains a black hole, white hole, and two universes. Derek, that's what you get when you push this map to its limits, so that every edge ends at a singularity or infinity. And in fact, there's another little feature in here, which is that little point there where they cross, that is an Einstein-Rosen bridge. To see it, we need to change coordinates. Now this line is at constant crustal time, and it connects the space of both universes. You can see what the space-time is like by following this line from right to left. Far away from the event horizon, space-time is basically flat. But as you get closer to the event horizon, space-time starts to curve more and more. At this cross, you are at the event horizon. And if you go beyond it, you end up in the parallel universe that gives you a wormhole that looks like this. So that is hypothetically how we could use a black hole to travel from one universe to another. Hypothetically, because these wormholes aren't actually stable in time, it's a bit like a bridge, but it's a bridge that is long and then becomes shorter and then becomes long again. And if you try to traverse this bridge, at some point, the bridge is only very short, right? And you say, oh, well, let me just cross this bridge. But as you start crossing the bridge and start running, your speed is finite, right? The speed of light roughly, and then the bridge starts, becoming stretching, and you never come out the other side. This pinching off always happens too fast for anything to travel through. You can also see this if you look at the Penrose diagram, because when you're inside one universe, there isn't a light cone that can take you to the other universe. The only way to do that would be to travel faster than light, but there might be another way. Schwarzschild's solution describes a black hole that doesn't rotate, yet every star does rotate, and since angular momentum must be conserved, every black hole must also be rotating. While Schwarzschild found his solution within weeks after Einstein published his equations, solving them for a spinning mass turned out to be much harder. Physicists tried, but 10 years after Schwarzschild's solution, they still hadn't solved it. 10 years turned into 20, which turned into 40. And then in 1963, Roy Kerr found the solution to Einstein's equations for a spinning black hole. which is far more complicated than Schwarzschild's solution, and this comes with a few dramatic changes. The first is that the structure is completely different. The black hole now consists of several layers. It's also not spherically symmetric anymore. This happens because the rotation causes it to bulge around the equator, so it's only symmetric about its axis of spin. Alessandro from Science Click simulated what happens around this spinning black hole. Space gets dragged around with the black hole, taking you and the particles along with it. When you get closer, space gets dragged around faster and faster until it goes around faster than the speed of light. You've now entered into the first new region, the ergosphere. No matter how hard you fire your rockets here, it's impossible to stay still relative to distant stars. But because space doesn't flow directly inward, you can still escape the black hole. When you travel in further, you go through the next layer, the outer horizon, the point of no return. Here you can only go inwards, but as you get dragged in deeper and deeper, something crazy happens. You enter another region, one where you can move around freely again, so you're not doomed to the singularity. You're now inside the inner event horizon. Here you can actually see the singularity. In a normal black hole, it's a point, but in a rotating black hole, it actually expands out to be a ring. And there are weird things happen with space-time inside the center of a black hole, a rotating black hole, but it's thought that you can actually fly through the singularity. We need a Penrose diagram of a spinning black hole, where before the singularity was a horizontal line at the top here. The singularity lifts up and moves to the sides, revealing this new region inside the inner horizon. Here we can move around freely and avoid the singularity, but these edges aren't at infinity or a singularity, so there must be something beyond them. Well, when you venture further, you could find yourself in a white hole, which would push you out into a whole nother universe. You can have these pictures whereby you're in one universe. You fall into a rotating black hole. You fly through the singularity, and you pop out into a new universe from a white hole, and then you can just continue playing this game, extending this diagram infinitely far. But there is still one thing we haven't done: brave the singularity. So you aim straight towards the center of the ring and head off towards it. But rather than time ending, you now find yourself in universe, the strange universe, one where gravity pushes instead of pulls. This is known as an antiverse. If that's too weird, you can always jump back across the singularity and return to a universe with normal gravity. And I know this is basically science fiction, right? But if you take the solutions of relativity essentially at face value and add on a little bit, which is what Penrose does here. He says this: oh look, these shapes are very similar. I can just stick these together. Then this is the conclusion that you get. Now we have effectively an infinite number of universes all connected with black hole, white holes all the way through, and you go to explore. But it'll be a very brave person who's the first one who's going to leap into a rotating black hole to find out if this is correct. Derek chuckles. Yeah, I would not sign up for that. So could these maximally extended Schwarzschild and Kerr solutions actually exist in nature? Well, there are some issues. Both the extended Schwarzschild and Kerr solutions are solutions of eternal black holes in an empty universe. As you say, it's an eternal solution, so it stretches infinitely far into the past and infinitely far into the future. And so there's no formation mechanism in there. It's just a static solution. And I think that is part of the reason why black holes are realized in our universe and white holes aren't, or might not be, I'm reasonably confident that they don't exist, right? Derek. For the maximally extended Kerr solution, there's also another problem. If you're an immortal astronaut inside the universe, you can send light into the black hole, but because there's infinite time compressed in this top corner, you can pile up light along this edge, which creates an infinite flux of energy along the inner horizon. This concentration of energy then creates its own singularity, sealing off the ring singularity and beyond. My suspicion and the suspicion of some other people in the field is that this inner horizon will become singular, and you will not be able to go through these second copies. So all the white holes, wormholes, other universes, and anti-universes disappear. There exists a kind of matter so strange, so defiant, that it challenges the very laws of physics themselves. Scientists call it exotic matter, but even among them, many find the idea hard to believe. One physicist once said, "I have a prejudice that such matter simply cannot exist." What troubles him is how often people claim that wormholes, those gateways between worlds in science fiction, are mathematically possible. And he admits, yes, that part is true. Mathematically, there are geometries of space-time that could, in theory, connect distant corners of the universe. But then he adds, almost with a sigh, Einstein's theory isn't just about geometry, it's geometry in the field equations. When you apply the real properties of matter, the kind we actually know, those bridges collapse. According to our best understanding, white holes, traversable wormholes, and parallel universes likely don't exist at all. Yet, there was once a time when we said the same thing about black holes, and then the universe proved us wrong. Perhaps one day what seems impossible now will become undeniable truth. As one scientist half-jokingly whispered, "We have one universe, right? Then why not two?" And so, as the night fades and the stars keep their quiet watch, we are left with more questions than answers. Perhaps the universe still hides doors we were never meant to open, or maybe, just maybe, it's waiting for us to knock. If you found a spark of wonder in tonight's story, stay close and let Midnight History guide you again through the silence between worlds. Subscribe, and together, we'll keep listening to the whispers of time.